Analyze the continuous beam shown in figure and find the moments at support B and C. The supports B and C sink down by 150 by EI and 75 by EI kilonewton meter respectively. Apply the flexibility matrix method. Here A to B, that is 10 meter, and is subjected to a point load of 20 kilonewton at a distance of 5 meter from the hinged support A with the moment of inertia for span is 2I. B to C, it is 10 meter with moment of inertia 3I, and is subjected to a point load of 30 kilonewton at a distance of 5 meter from either end. In span CD, D is the end support which is on roller. The total span is 10 meter with moment of inertia I and is subjected to a load of 10 kilonewton at a distance of 5 meter from either end. First you have to calculate the degree of redundancy. Here support end A is, the support at end A is hinge and D is on roller, and the intermediate supports B and C are on rollers. Here the number of unknowns, no horizontal forces are acting, hence no need to consider horizontal force. At end support A, VA is the only one reaction component acting vertically upward. At B, either VB or MB is the moment or VB is the reaction acting vertically upward. At interior support C, either VC or MC as the unknown. At end support D, that is on roller, PD is the only unknown. Then the number of unknowns are 4. Number of available equations of equilibrium, that equals to, one is summation of V equals 0 and one is summation of M equals 0. Therefore, the degree of redundancy is 4 minus 2, that is 2. Here you may consider any 2 as the redundant, any 2 convenient unknowns as the redundant. Now we'll consider MB and MC as the redundants in the above figure. Now we will remove the redundants. After removing the redundants, we will make it the stable and determinate structure by removing the redundant forces or redundant reactions. Here first we have to calculate the displacement due to the applied loads. Here release the structure and remove the redundants and draw the release structure, make it determinate and stable. Here in span AB, that is subjected to a point load of 20 kilonewton with moment of inertia 2I. In span BC, here this is subjected to 30 kilonewton with moment of inertia 3I, and this is CD with span 10 meter and subjected to 10 kilonewton with moment of inertia I. Here give the coordinate numbers. Here we have considered MB and MC as the redundants, hence we have given MB in place of MB we have given the coordinate number 1. In place of MC we have given the coordinate number 2. Now we have to find the displacement due to the applied loads at coordinate 1 and 2. That is, here delta L1, displacement due to the loads at coordinate 1. Here two spans are connected, one is BA, one is BC. Here due to the applied loads it will undergo deformation like this. Here this is the slope at or the displacement at B due to the applied load. Similarly in this span this is the displacement due to the applied load at coordinate 1. Then delta L1 equals WL square divided by 16 EI for span BA plus WL square divided by 16EI for span BC. By substituting the values of W and L, W, L and I, then we will get for delta L1, that is 20 into 10 square divided by 16E. The moment of inertia is 2I for span BA, plus 30 into 10 square divided by 16E. The moment of inertia is 3I for span BC. By simplification, that is 125 by EI. Then the displacement at 2 due to the applied load, that is, here two members are connected, one is CB, one is CD. Then we have to calculate the displacement in span CB and in span CD due to the applied load. Here, that is WL square divided by 16EI for span CB plus WL square divided by 16EI for span CD. Then by substituting the values for CB, load is 30, span is 10, W into L square divided by 16E, moment of inertia is 3I. Then for span CD, load is 10, span is 10 square divided by 16E, moment of inertia is I. Then after simplification, it is also 125 by EI. The third step is to find out the displacement due to the sinking and settlement of the supports. Here the support B and C, there is a settlement of 150 by EI at support B. Similarly at support C there is a settlement of the 75 by EI. Then we have to find the additional moments due to the sinking and settlement of the supports. You know that the fixed end moments due to the sinking and settlement of the support is given by minus 6 EI delta by L square. By using that, we can calculate the additional fixed end moments due to the sinking and settlement of the supports. The various supports, that is, here M dash F AB, that is additional fixed end moment due to the settlement in span AB, that equals M dash FBA, that equals minus 6 EI delta by L square. Here, by observing this diagram, the relative settlement with respect to B, with respect to A, B is settled down by an amount of 150 by EI. 150 by EI. Here, with respect to the horizontal, the rotation is clockwise, hence delta is positive, then that is minus 6 EI delta 1 by L square. Here delta L1 is 150 by EI. By substituting the values, that is minus 6E into 2I, the moment of inertia is 2I, into the delta 1, that is 150 by EI divided by L square. Here you will get an additional moment of minus 18 kilonewton meter. Similarly for span BC, B to C, with respect to C, there is a relative settlement of, that is 150 minus 75, that is 75 by EI. Here the rotation with respect to the horizontal drawn, here the rotation is anti-clockwise, hence the settlement is negative, that is by using M dash FBC equals M dash FCB, by using the equation minus 6 EI delta 2 by L square. By substituting the values for span BC, that is minus 6E into 3I divided by L square into minus 75. Minus into minus, that becomes plus, that is EI get cancels. The additional fixed end moment due to the settlement of the support, here this becomes minus into minus plus, that is 13.5 kilonewton meter. Then in span CD, here there is a relative settlement with respect to D. C is moved in downward direction, or the rotation is in anti-clockwise direction, hence that is also the settlement is negative. Then M dash FCD that equals m dash FDC, that equals minus 6 EI delta 3 by L square. Then by substituting the values, minus 6 EI into minus 75 by EI divided by 10 square, minus into minus, that becomes plus, that is 4.5 kilonewton meter. Here these are the additional fixed end moments. Here, due to these fixed end moments, there will be the rotation at A. This one is the additional fixed end moment due to settlement of the support. This one is here, this is that is anti-clockwise. Then this one is also anti-clockwise, that is minus 18 kilonewton meter, that is in span AB, that is 18 kilonewton meter at both the ends, that is anti-clockwise. Then in span BC, here there is a clockwise moment of 13.5 kilonewton meter. In span CD, there is a clockwise moment of 4.5 kilonewton meter. Here, due to this additional fixed end moments, we have to calculate the displacement at coordinates 1 and 2. Coordinates 1 and 2. Now, we can calculate the additional fixed end moments, that is delta 1. Delta 1 equals here in span BA, that is, and in span BC. Here ML by 3EI for span BA, ML by 3EI 6EI in span BA plus ML by 3EI in span BC, ML by 6EI for span BC, due to the two moments here, this one and this one and this one, due to these two moments here there is a at B. Here there are two spans, one is BA, one is BC, and due to these two moments the displacement at B. Similarly, due to this is hogging moment, this is sagging moment, here this is sagging moment, here this is hogging moment. Here due to these moments we have to calculate the total slope at B, that is due to this one, that is 18 ml divided by 6EI, due to this one, that is ml by 3EI for this span BA. Then for this span BC, that is ml by 3EI due to 13.5 and ml by 6EI due to 13.5. Here we have calculated the moments like this, the displacement like this, that is ml by 3EI in span BA, ml by 6EI by in span BA, ml by 3EI in span BC, ml by 6EI in span BC. Here 18 into 10 divided by 3 into 2i, that is similarly minus 18 into 10 into 6 e divided by 6 e into 2i plus 13.5 into 10 divided by 3 into 3i minus 13.5 into 10 divided by 6e into 3i. Here we will get delta 1, that is the displacement due to the additional fixed end moment at coordinate 1 is 22.5 by ei. Similarly, delta 2, that is theta cb plus theta cd, the net moment at coordinate 2 due to the two moments, that is ml by 3ei plus ml by 6ei in span cb, ml by 3ei, ml by 6ei in span cd. That is, by substituting the values here, 13.5 is minus 13.5 into 10 divided by 3 into 3i in span cb, 13.5 into 10 into 6e divided by 6e 3i. Here this becomes delta 2 becomes 0. Here now we have got the values of the additional due to the additional moments, we have got the displacement at coordinate 1 and 2 respectively. Here now we can write the displacement vector caused by the sinking and due to the loads. Here delta minus delta L is the vector due to the settlement and due to the applied load, the displacement due to the applied loads. Here we will get the 22.5 minus 12.5, that is minus 125, that is minus 102.5. Here 0 minus 125, that is minus 125 by EI. Now the flexibility matrix, the elements of flexibility matrix were given by here by removing the applied loads, and now we can apply the unit rotation by assuming the direction of the moments, redundant moments at MB at 1 and 2, that is apply separately. Now we can apply the redundant in place of redundant moment MB. Here we can apply a unit hogging moment at coordinate 1. Here the two spans are connected, one is AB, one is BC. Then F11, that is the flexibility matrix element, that is displacement at 1 due to the load at 1. Here we have to calculate the displacement in both the spans, that is ML by 3EI for span BA, ML by 3EI for span BC. That is the span for span length for BA, that is 10, since the moment is hogging minus 1 into 10 divided by 3E, the moment of inertia is 2I. For span BC, the span is 10 minus 1 into 10 divided by 3E into 3I, moment of inertia is 3I. After simplification, here we will get, that is minus 25 by 9 EI. Then by F21, displacement at 2 due to the load applied at 1, that is F21, that is ML by 6 EI in span C to B, that is minus 1 into 10 divided by 6E into 3I, that is minus 5 by 9 EI. Now we can apply the unit moment in at coordinate 2 in place of the redundant MC. Then here this one is 1 kilonewton meter, that is here we can assume the direction of the redundant. In place of redundant we can apply the unit moment, hogging moment. Then F12, displacement at 1 due to the unit moment applied at 2, that one is minus ML by 6 EI, that is by substituting the values minus 1 into 10 divided by 6E, the moment of inertia for this span is 3I, that is minus 5 by 9 EI. By Maxwell's reciprocal theorem of deflection, F21 and F12 both should be equal. Then F22 is the displacement at 2 due to the load applied at 2. Here two spans are connected, one is CB, one is CD. Then ML by 3 EI for span CB, ML by 3 EI for span CD. Then minus 1 into 10 divided by 3E, the moment of inertia for this span is 3I. Then minus 1 into 10 divided by moment of inertia is single I, that is 3EI. By simplification, that is minus 40 by 9 EI. Now after getting the flexibility elements, we are able to write the flexibility matrix, that is the elements are F11, F12, F21, F22. Then minus 1 over EI is common, remove it outside. Then the elements are 25 by 9, 5 by 9, 5 by 9 and 40 by 9. Now the final moments, we know that the redundant matrix is given by inverse of flexibility matrix into the displacement factor due to sinking and settlement of the support minus the displacement due to the applied loads. Then here the redundants we have considered are MB and MC, the elements of redundant matrix, that is MB and MC, that equals inverse of minus 1 over EI is minus EI. Inverse of flexibility matrix, that is 25 by 9, 5 by 9, 5 by 9, 40 by 9 into the net settlement, net displacement matrix, that is already we have got that is minus 102.5 minus 125 1 over EI get cancels. After simplification, you will get the value of MB and MC. MB equals 32.077 kilonewton meter. MC equals 24.115 kilonewton meter. This one is hogging moment, that is 32.077 kilonewton meter. Now we can draw here the answers are, both the answers are positive, that means our assumed directions are correct. Then we can easily draw the bending moment diagram. That is, here the support moments 32.077 at this point, B at this point 24.11 kilonewton meter. Just now we have calculated. Now we can easily draw the bending moment diagram. Here this one is at A, bending moment is 0, support moment at B, that is 32.077, that is hogging. Hence join these 2 points by a straight line. This is the reference line. Above the reference line, draw an ordinate of 32.077 kilonewton meter. Then similarly at support C, the bending moment is hogging, that is 24.115. Draw the ordinate of 24.115 and join these 2 points by a straight line. Here at support it is 0. Then the simply supported beam bending moment. Simply supported beam bending moments are, this one is 20 into 10 by 4. That one is 50 kilonewton meter. That is W into L by 4. This one is 30 into 10 by 4. Here the maximum bending moment occurs below the point load. At the support the bending moment is 0. That is at the support WL by 4, that is 20 into 10 divided by 4. That one is 200 by 4, 50 kilonewton meter. Here this one is positive bending moment, this one is negative bending moment. At the center it is positive, at the support it is negative. Then this one is 75 kilonewton meter. That is below the point load the bending moment is maximum, that is the magnitude of that one is 75 kilonewton meter. At the support the bending moment is 0. Here below the point load, that is 10 into 10 divided by 4, this one is 25 kilonewton meter. This is the shaded portion, give us the net bending moment diagram. Here this is the bending moment diagram. We'll continue in the next video.